Hello everyone, I'm Yong from Tsinghua University, China. I'm currently visiting MIT as a visiting PhD student and working with Auden. It's my pleasure to give a presentation about the topic of capacity value of demand-side UPS storage. Let's start with the background and motivation. Nowadays, the penetration of renewable energy is continuously increasing to replace fossil fuels and promote carbon reduction. Meanwhile, in modern power systems, new types of electricity consumers, such as base stations and data centers, are increasing. These consumers are equipped with UPS storage for reliability issues. In the future, the amount of installed UPS storage is unignorable. On the one hand, with the increasing of renewable energy, it brings more uncertainties to power systems, so more flexible resources are needed. On the other hand, battery energy storage is a promising kind of flexible resources. So the question is, can we make use of UPS storage to provide flexibility to power systems? Our previous work has shown that while providing reliability backup, some UPS storage facilities can have spare capacity that can participate in power systems, especially in high power supply reliability areas. And our previous work has also studied how to dispatch them or how to organize them to participate in the power system frequency regulation. And in this research, we just want to exhibit the contributions of UPS storage to power system load carrying ability. The contributions of UPS storage to power system load carrying ability is represented using capacity value. The concept of renewable energy capacity value has been widely applied in different power system analysis scenarios, and the capacity value of energy storage has also been studied by several researchers. But the capacity value of UPS storage hasn't been properly studied. The capacity value has several metrics. In this research, the effective load carrying capacity, that's ELCC, is used. The ELCC of UPS storage can be described as the amount of additional load that can be supplied by the power system, considering UPS storage, while preserving the reliability level. And on the right, there is an illustrative figure to show this concept. And this amount is the ELCC. About the framework, we just propose a three-stage framework to estimate the ELCC of the UPS storage. And at the first stage, the power system operator just calculates the system-level reliability indices without UPS storage using the sequential Monte Carlo simulation. So they just provide a benchmark. And at the second stage, each UPS storage owner just determines the operation policy of its UPS devices through a stochastic dynamic programming model, respectively. And at the third stage, the sequential Monte Carlo simulation, while considering the operation of UPS storage, is conducted to estimate the ELCC. And for the first stage, calculate the system-level reliability indices without UPS storage. We should first build the reliability models. For the conventional generators, we just use the two-state Markov model. And for the renewable energy, for example, the wind power or solar power, we can use the historical data, or we just generate new data using some renewable energy output model. And for the power load, we just sample from the historical data. and the reliability evaluation time horizon is 1 year, and the sampling density is 1 point per hour. Here gives a simple flowchart of the sequential Monte Carlo simulation. At the first part, we just sampling from our reliability models. For example, for conventional generators, we just sampling from the Markov model. And for renewable energy and power loads, we just sampling from the obtained time series. And then in the second part, we just analyze the obtained samples. For each sample, we just judge whether the loads can be served by the generators or not. If we denote Gi and Di as the total generation capacity and the total power load at the I sample, we can just compare Gi and Di to find that at this sample, whether all the loads can be served or not. Then, as the third part, we just test the convergence. And if the Monte Carlo simulation is converged at the current state, we just output the evaluation results. And if not, we just return back to the first part to generate more samples and analyze them, and then we retest the convergence. And it's just a loop until the convergence is reached. And here we use the reliability indices as the expected energy not served, that's EENS, and it provides the benchmark for the reliability level that without the UPS storage. And we also provide the mean time to failure and the mean time to repair indices for the following steps. Then we move to the second stage, is to determine the UPS storage operation policy respectively. Here we use a stochastic dynamic programming model. The reason is that solving the stochastic dynamic programming can provide policies that can be used in different scenarios, so it avoids repeatedly running optimization to obtain the state of charge of storage in each sample in the Monte Carlo simulation, so it's much more time efficient. Here provides some model details about the stochastic dynamic programming. The decision stages of the stochastic dynamic programming is a time theory and is not continuous. And the state variables at each time slot is the state of charge of the UPS storage, the electricity price, and the power system status. Here, CT and XT are exogenous variables that comes from the power system, and XT represents the system status. If XT equals to 1, it means that there is a power shortage in the system. And if XT equals to 0, it means that there is no power shortage at this time slot. And the decision variables for the model is the charge power and discharge power of each UPS storage. And for the constraints of the model, we have several constraints here. And the first part of them just representing the UPS storage's feasible operation region. And the second part just preventing the storage from charging and discharging simultaneously. The details of the constraints can be found in our previous work. And here is a figure to show the operation region for the UPS storage. We can see from the figure that with different time slots, the dispatchable capacity that can be used is changing. So we should operate it in a time varying operation region. And the state transitions of the stochastic dynamic programming model can be divided into two parts. The first part is the deterministic part. It describes the energy conservation relationship of the UPS storage. And the second part is the stochastic part. It represents the uncertainties of power system shortages. We construct a two-state discrete time Markov process to represent it. And the parameters of the Markov process comes from the MTTF and MTTR obtained in the first stage. As for the optimization target, we denote the state of time slot t as st, and the reward function of time slot t consists of two parts. The first part is the temporal arbitrage during the normal time, and the second part is the reward from carrying load during shortages. So we use this optimization target to let the UPS storage to do temporal arbitrage if there is no shortage happens. And if a shortage happens, we organize them to carry load as much as possible. The value function at time slot t can be represented as this. And if we apply the Bellman equation, we can change it as this one. Then after that, we can solve this stochastic dynamic programming model. We just discrete the state space and decision variables and use the backward recursion method, which is commonly used in solving dynamic programming models. Then we can get a policy table for any time slot and any possible states. Then we come to the third stage, that's evaluate the ELCC. We also use the sequential Monte Carlo simulation here, but we just evaluate the reliability with the UPS storage. So the most part are the same with the sequential Monte Carlo simulation in the first stage, but the operation of UPS storage facilities are considered here. And moreover, we add additional load delta D to the system. And according to the definition of the ELCC, so if the ENS here equals to the benchmark ENS, then the delta D is the ELCC of this UPS storage. Here we can recall this figure, and this one is the benchmark ELCC. And if we add more and more additional loads to the system, and the ENS increases, and at this point, the ELCC equals to the benchmark. So this one is the ELCC of UPS storage. We can use the binary search method to find this delta D and to find the ELCC. As for the case study, we just test this framework on a modified IEEE RTS system. We add some renewable energies to the system, and we also add some UPS storage to it. Then we just test the performances. Here is the illustrative operation of a UPS storage in a typical day. We set the hour 3 to 5 as the power shortage hours. So during hour 3 to 5, the UPS storage discharges with the best of its capacity to help the system carry loads. And after this shortage, the UPS storage just charges for the SOC recovery. And in other hours, we can see that the UPS storage conducts temporal arbitrage and according to these electricity prices. And we also test the ELCC under different settings. Here is a figure. The x-axis is the UPS installed capacity and the y-axis is the ELCC. We can see from the picture that ELCC improves with the increase of UPS storage, power, and energy capacities. And I also want to point out that if we only have a 3-hour UPS, the most part of the capacity need to be reserved for the reliability issues. So only a few parts can be dispatched by the power system. So its ELCC is very low. But if the duration improves, and we can have more ELCC. And that's all. Thank you for your listening.